We're going to look at the integral test here, which is a way to determine if an infinite series converges. Then later on we'll use the integral test to talk about P-series. The idea behind the integral test is you'll take some series, in this case I'm giving you a specific example, but you'll compare the terms of that series to the actual area under a curve that is the same function as the function inside the series. So if you look at this one, I've got my curve, and I'm actually using right-handed Riemann sums. And you'll notice that the area, if I did right-handed Riemann sums, my first rectangle has an area of 1, then 1/4. My next rectangle has an area of 1/9. My next rectangle has an area of 1/16, so on and so forth. You can see that that right-handed Riemann sum actually is the same series as n goes from 1 to infinity of 1 over n squared. So the right-handed Riemann sum will give you the series. Also, you can look at this curve in the graph and tell that the area given by the Riemann sums is less than the actual area, the true area under the curve, from 0 to infinity. So the idea behind the integral test is rather than look at the series, we're going to look at this improper integral and determine if the integral converges, which we know how to do improper integrals. Now this integral actually has improper behavior at both ends. We have a vertical asymptote at 0 and we're approaching infinity. So what I'm going to do so that I only have improper behavior at one end of my area, I'm going to separate out that first rectangle of 1, and I'm actually going to see what's happening with my series as n goes from 2 to infinity of 1 over n squared. Because if I can determine that the series from 2 to infinity converges, then adding 1 to it is not going to affect the convergence of it. Now, since I'm going from this term starting with 1/4, I'm actually going to compare that, and I know that that series is less than the area from 1 to infinity, and by doing that, making that one little change, I now can do this as an improper integral. So again, our challenge is to determine if this converges. And we know how to do improper integrals. So let's go to the next page, and we will find out whether this integral converges. If the area actually does exist and my series is less than that, then the series would by default have to converge as well. So here's the integral we're trying to work with. Remember, the first step to an improper integral is always to convert it to a limit. So I'm going to change that to the limit as t approaches infinity of 1 to t of, I'll go ahead and make that x to the -2 dx, and then we'll integrate that. This is a fairly easy one. -1 over x from 1 to t, which is -1 over t minus -1 over 1, which actually make it +1. So I did the integral, plugged in my limits, and now I'm going to find the limit as t approaches infinity, and this thing equals 1. So what I've determined is that the area under the function, the true area from 1 to infinity, is actually 1, and we know that my series is even less than that. So we'll pull that onto the next page. There we go. And so we knew that the series from 2 to infinity was less than that, so this is less than 1. My actual series from 2 to infinity. But remember, we were more interested in the series from 1 to infinity. The original problem was starting at 1, not starting at 2. But by starting at 2, all I did is I omitted the term of a 1, that first term 1, so I'll simply add 1 to both sides. And what I can say now is that my series as n goes from 1 to infinity of 1 over n squared is less than 2 when we account for that first term that was omitted. We don't know what it converges to, but we have now determined that this series is less than 2, which means it will converge, therefore converge. Yay. All right, so that's the idea behind the integral test. Now that was an example. We probably won't go into that much detail how I separated out the first term. The integral test actually is fairly straightforward. Here is the formal definition. And first, the integral test is only applicable if your function is continuous and if it eventually is always positive and decreasing. It may have some funny behavior at the beginning, the first few terms, but as long as eventually it is positive and decreasing, then you can use the integral test. And the integral test simply says that, and I'm not going to read all of that, but it says that if the improper integral for your series n equals k to infinity, if the improper integral k to infinity converges, so does your series. If k to infinity f of x dx diverges, then so does your series. So whatever the integral does, the antiderivative does, so does your series. And remember, your function must be continuous, positive, and decreasing. So the first thing you want to do is make sure that your function actually satisfies those three pieces of information. So let's do one specific example of this, determine whether this function converges or diverges. First, I do know that my function, if I were to look at the function ln x over x, I do know that it's positive. From 1 to infinity, and I know that it's continuous from 1 to infinity. There is a discontinuity at 0, but I don't care about 0 because I'm starting with n equals 1. It's going to be a little bit of a challenge to prove that this is decreasing. So let's show that this decreases. Normally, to show that something decreases, all you need to show is that for any two consecutive terms, the n plus first term is less than the nth term. And a lot of times that's fairly easy to do. In this case, if I tried the n plus first term, the natural log of n plus 1 over n plus 1, is that always going to be less than the natural log of n over n? And to be quite honest with you, I can't tell right off the bat whether or not that's true, because both numerator and denominator are changing. There are some times, like that example we had earlier, and I'm going to erase this in a second, where I had 1 over n squared. I could show that that decreases fairly quickly because 1 over n plus 1 squared is indeed less than 1 over n squared. My n plus first term is less than my nth term because my denominator is bigger over here while the numerator stayed the same. So a lot of times you could simply do a sub n plus 1 and compare it to a sub n to know something decreases. This function is not one of them that's that easy. So the other way we can show that something decreases is by looking at its first derivative and show that f prime is negative. So this is inconclusive. So now I'm going to show that f prime of x is negative. If f prime of x is negative or eventually negative, then we know this function would decrease. So let's find the derivative real quick, assuming you know how to find derivatives. That's going to be low d high, which ends up being 1, minus high d low is just natural log x over low x squared. So there's my derivative, and I want to know when that thing equals 0. Well, I know it equals 0 at x equals e. And then if you do the little sign chart thing, e is my critical number. I know my critical number gives me a 0 for my derivative, so maybe I'll plug in 1, and I'll plug in something huge, 47. 1 minus natural log of 1 over 1 squared is positive. If I plug in something huge, natural log of something big will eventually be larger than 1, so it'll be negative. And what happens is my function does decrease. My function does decrease on the interval e to infinity. And remember, as long as it is ultimately decreasing, then we can use the integral test. I realize the function increases for n equals 1 and n equals 2, but the second I pass e, this thing is decreasing, therefore we can use the integral test. So now we'll go to the next page and we'll actually find the antiderivative from 1 to infinity of ln x over x, and we'll see what that gives us. So we need to find the antiderivative from 1 to infinity, natural log x over x. If we get a finite answer for this, then my series converges. If I do not, if this diverges, then the series will also diverge. This one is a u sub problem. Since you should know the antiderivative, I'm going to skip showing you the details and go right to the antiderivative. There we go. You can see I did my u sub over there for those of you who wanted to see how I got to this. So I converted it to a limit. Remember, you must write it as a limit, then work out the antiderivative. I'm now down to computing the limit as t approaches infinity. And as t approaches infinity, this is the natural log of infinity squared over 2, which is infinity, minus natural log of 1, which is 0. This ultimately is infinity, which means this area diverges, which means that my original series, as n goes from 1 to infinity, oh, was it 1 to infinity? Yeah, that'll work. Never mind, I'm being stupid. ln n over n diverges. And there's our conclusion. So you simply find the improper integral, and if that converges, then so does your series. In this case, the improper integral diverged, so the series also diverged. Now, closely related to the integral test are little babies created by the integral test called P-series. These are series that you're expected to just know and to determine their convergence by simply looking at it. If you want to, you are allowed to, you could use the integral test to prove that these converge. But in short, a P-series is a function, or a series, that is 1 over n to some exponent. A P-series will always converge if the exponent on n is greater than 1. It will always diverge if the exponent on n is less than or equal to 1. And that's all there is to it. Now, yeah, we'll talk about the ugly stuff with that later. Now, so, I'm trying to regather my thoughts here. So a few P-series. Right here we have 1 over n to the 4th. In this case, this is a P-series. P is equal to 4. 4 is greater than 1. Therefore, converge. That's all there is to a P-series. In this one, 1 over the square root of n, your exponent on n is 1/2, which is less than 1. Therefore, that diverges. If your exponent is greater than 1, the P-series converges. Exponent less than or equal to 1, diverge. Here, 3 over n. If you wanted to kill this dead, you could rewrite that as 3 over, or 3 times the series from 1 to infinity of 1 over n. And in this case, this is p equal 1, also known as the harmonic series. That is a harmonic series, and that means this will diverge, which we have talked about the harmonic series in the past, but now this is another way that you know it diverges. A few minutes ago, I kind of stumbled over my words and hesitated, and there was this awkward few seconds of silence. I was going to point out that P-series are specifically 1 over, or maybe even a constant over n to the 4th with nothing else in the denominator. So if you have something like 1 over n cubed plus 3, technically that's not a P-series because of the plus 3. We'll have to use a method called direct comparison to see what happens with that. So just a little side note that this is not technically a P-series, although it very, very, very closely resembles one, and it will end up converging because 1 over n cubed also converges. But for that weird hesitancy I had a few minutes ago, this is what was going on in my mind. Just know that P-series are specifically a constant over simply n to an exponent with nothing else. So there we go. That's P-series and the integral test, and I will stop there.